So today we are going to discuss a topic on deep learning, which is forward pass, and how to use the parameters involved or found in a forward pass and use them to calculate the backward pass or backpropagation. We are going to see these concepts through and worked out example. Now let's go through it. Here we can see one figure which is given as, in this figure we can clearly see the x is an input variable in R3. Then we get the input as 3 neuron, then the weight vector, and we'll get with the x and w will get pre-activation h1. Then using the log function we'll get h1, which is an activation, and h1 will now work as input for w2, which is weight vector for second hidden neuron or second hidden layer, and we'll get a2, which is second pre-activation, and using log function again on a2, for each a2 will get corresponding h2 activation, and this will each value of h2, here we can see 3 value will get 3 value of h2, and this 3 value will act as an input in w3, and we will get finally a3. And after a3 we'll use the softmax function, and we will get the output result. Now, and from the output result we can calculate the log function, and afterward we will use the differentiation or del operation to calculate the backpropagation. Now let's start. The first thing is well, some given parameters are w1, w2, w3, and b1, b2, b3. w1, w2, w3 are the weight vector. We can see it is 3 by 3 matrices, and these biases terms are the column vector. Now, for the forward pass, the first formula which we will use is to calculate A1, which is nothing but the pre-activation. So we can see it in a diagram using X, which is also known as H naught. And this is H1, so this is H naught. First input are also X, and W1 and the bias term B1 will get A1. W1 multiplied by X plus B1. This is W1 and X is matrix multiplication. X is already given, and I think, yeah, here X is given, which is a input vector 1 0 1. This is a column vector, and the corresponding Y is 0 0 1. This is also given. Now for the forward pass we will calculate this matrix multiplication and then add to it, and we will get column vector. Now for simplicity I have used the dot dot symbol, but you can look in this figure to go through each value, and if you calculate you will get what I have got it in the A1 column vector. That is all right. So there's nothing to be worried. I just use dot dot because it is too cumbersome to write again and again. Now using the logistic function, which is 1 by 1 plus e to the power minus ai, in this particular case we will get a column vector of ai. So for each ai we will use this 1 by 1 plus e to the power minus 1.5350184 like this. Next one 1 by 1 plus e to the power minus 1.998250233, and in the last one 1 by 1 plus e to the power minus 1.9304489. If you do the calculation, and we will get the h1 column vector as this one. So we get the first pre-activation using the logistic function. We get the activation. Now what we need to calculate is second pre-activation or second hidden layer using W2 and H1. Now H1 will be our new input vector. We use formula A2 is equal to W2 H1 plus B2. Again, it is similar to A1, the formula. And again, I have used dot symbol, but you can go through this slide again and you can carry out the calculation. You will get the result as a column vector, which is 2.1416, and second one is 1.27820,435, and third one is 3.03985175. So after this, what we need to do is to calculate H2 using the logistic function. Again, we put 1 by 1 plus e to the power minus 2.14168566, then 1 by 1 plus e to the power minus 1.27820,435, and for the third one, 1 by 1 plus e to the power minus 3.03985175. And if you use the calculation correctly, and we will get the column vector which is like this. Now so what we need to do, like the third pre-activation, the formula is similar to A2 and A1. A3 is W3 H2. W3 is third weight vector, and H2 is second activation, not pre-activation, plus the third bias term. And if you use the calculation, we'll get the result as like a column vector which is 1.31161045. Second one is 1.66816384, and third one is 1.8956353. And for the last or the final output, we use the softmax function on A3, the pre-activation, and we will calculate H3, which is nothing but e to the power 8 A3i. Well, A3i is 8. For every term, we'll calculate its value of softmax, which will be calculated as e to the power 1.31161045 divided by e to the power 1.31161045 plus e to the power 1.66816384 plus e to the power 1.8956353. So for the second one, which would be nothing but e to the power 1.66816384 divided by and this line again. And for third one, e to the power 1.8956353 divided by this summation again. So we will get the H3 column vector as this value, and then you will find a cross entropy loss. For this, we will use the output vector. If you take the transpose, this is similar to y. Now the function for evaluating cross entropy loss is equal to L is the loss is equal to minus summation of yi log of h3I or log of yi, which is nothing but minus log of 0.4247576y. Well, because in the final term, the only value which is 1 is in the third, and we can clearly see in H3 the third one in this column vector is 0.424, and uh, that's why we put this as inner log value. Now for y1, where yi is gone, well, yi is nothing but this one, y3 actually. The value which is given as 1, that will be our yi. So 1 multiplied by minus log of anything is only that thing, minus log of 0.424 dot dot dot. You can clearly see the number. So you can clearly see all the digits. So if you do the calculation, you will get 0.8561909. Now the back propagation. So in back propagation, we first use the differentiation of loss with respect to A3. So in forward pass, we will first calculate the first pre-activation, then activation, then second pre-activation, then activation, then like this was until we get the output. But for back propagation, we will try to evaluate the differentiation of loss with respect to the last pre-activation, or uh, then after that the second activation, then third the first activation. So it will that's why it is called back pass or back propagation. Let's see, it will be clear after looking at this example. So the formula for this is nothing but the subtraction of y cap minus y. So what are the y cap? Y cap which we already calculated, and this is the y cap. H3 is nothing but the y cap. This is the output. The what are the output we have calculated? It is the calculated output or predicted output, and this is the actual output. Y is actual output. H3 is the predicted output. So y cap is the predicted output and y is the actual output. If we subtract this from y cap, then we will get this result, and this is nothing but the differentiation of loss with respect to A3. Now what is the differentiation of loss del of L with respect to W3 or weight vector 3? Well, the formula for this is the loss with respect to A3 multiplied by H2 transpose. And if we calculate this matrix multiplication, this is a column vector and this is a row vector. If we multiply this, we'll get 3 by 3 matrix, which is differentiation of loss with respect to W3. And W, what is the differentiation of loss with respect to bias, third bias? Well, this is simply equal to loss with respect to differentiation of loss with respect to third pre-activation, there, which we already created. But why? Well, the reason is very simple. The reason is the gradient of loss with respect to B3 is same as gradient of loss with respect to A3, the third pre-activator. Since A3 is equal to the formula which we calculate A3 from W3H2 plus B3. So if we take the differentiation with respect to B3 of loss, this will be exactly equal to gradient of loss with respect to A3. all other things will be cancelled out. And also the reason is very simple. This is the linearly dependent. So A3 and B3 are linearly dependent. That is why. The next thing is uh, next thing we need to calculate gradient of loss with respect to H2, which is nothing but W3 or third weight vector transpose gradient of loss with respect to A3. The next is uh, we need to calculate the matrix multiplication, and here we can clearly see the value which they written in W3, what we got in gradient of loss by calculating gradient of loss with W3. We need to put this value, and, and W3 is here. Well, W3 is already given. W3 is this one, and we need to transpose this, so row vector become column vector, and column vector become row vector. And if we transpose this, and if we write it down and multiply it with gradient of loss with respect to A3, which is this one, we will get a column vector which is nothing but gradient of loss with respect to A2, H2, sorry, H2. The second second activation. Now, what is the gradient of loss with respect to A2? Well, this is nothing but gradient of loss with respect to H2 outer product differentiation of the log function when it is A2. And we already know the formula of differentiation of log function when it is A2 is nothing but H2 outer product 1 minus H2. How did we get H2? Well, H2 are the activation value. How we get H2 value? By using the log function. If we use the log function, so the formula was actually the differentiation of log function with respect to differentiation of loss function when it is A2 is nothing but loss function when it is A2 outer product 1 minus loss function when it is A2, and we know the loss function when it is A2 is H2, so we just substitute this in the first term. Now if we use this formula, then we can clearly write it down the H2 value and 1 minus H2 value, and we will get one column vector. This would be our differentiation of log function when it is A2. And how did you get H2? Well, while calculating the forward pass, you can go back and you can see by yourself. We have calculated H2 using A2 and using a function which is log function, which is nothing but 1 by 1 plus e to the power minus A2. Now, what will be the gradient of loss with respect to A2? Well, gradient of loss with respect to A2 will be outer product between gradient of loss with respect to H2 and differentiation of log when it is A2. We have calculated this one, differentiation of log loss with respect to when it is A2, and we have already calculated differentiation of gradient of loss when it is H2. You can go to the previous slide and we can see here this one. And if you do the outer product and you get one column vector again, which will be our A2, differentiation of loss with respect to A2, not A2. Then we need to calculate gradient of loss with respect to W2, second weight vector. This is nothing but gradient of loss with respect to A2 multiplied by H1 transpose. Well, we have calculated H1 using A1 and putting A1 values inside the log function, which is 1 by 1 plus e to the power minus A1. And we will use this transpose and we will get a transpose matrix, and in differentiation of loss with respect to A2 we have already calculated. You can put it here, and if we do the matrix multiplication, this column vector, this is one is a row vector, and we will get one 3 by 3 matrix again. And differentiation of loss with respect to B2, second bias type, will be equal to differentiation of loss with respect to A2, because A2 and B2 are linearly dependent, as A2 equal W2 or second weight vector into H1 plus B2. You can go back and see what was the formula. Next, so the next one is what is the gradient of loss with respect to H1. This is also the formula is again similar, gradient of loss with respect to H2 with respect to H2. So gradient of loss with respect to H1 is W2 transpose gradient of loss with respect to A2. Now we have already calculated gradient of loss with respect to A2, and W2 is already given. We will transpose this matrix and we will calculate this matrix multiplication, and we will get one column vector which will be look like this. Then we will calculate gradient of loss with respect to A1 with using the formula gradient of loss with respect to H1, the first activation, and the outer product with the differentiation of log function when it is A1. And we already know the formula of log function, differentiation of log function when it is x is nothing but log function when it is x multiplied by 1 minus log function when it is x. So if we take x as A1, then we will get log function when it is A1, outer product 1 minus log function when it is A1. Oh, we already know H1, the first activator, is nothing but when we use the log function to A1. So in the value of log function when it is A1, we will substitute as H1. So this formula will become differentiation of log function when it is A1 is equal to H1 outer product 1 minus H1. So we already know the H1 value. We have calculated it. You can go back and see the H1 value, and we will use this H1 and 1 minus H1 like this, and we will get one column vector. And we have also calculated this H1 and 1 minus H1. We have calculated this, and we will get this gradient of loss with gradient of log loss with respect to A1. Now we are going to use this value in order to calculate gradient of loss with respect to A1. We have already calculated gradient of loss with respect to H1. You can see it in here. So we are going to use both of these column vector, and we will get one column vector which is gradient of loss with respect to A1. Now from this we will going to calculate gradient of loss with respect to W1. So you can clearly see where from where we are coming and where we are going. So we have calculated first gradient of loss with respect to A3, then W3, then H2, then A2, then W3, then H1. It will go like this. And in between of this, we have calculated gradient of loss with respect to B3 and B2 also. So I think we are in here. So from this we are going to calculate and gradient of loss with respect to W1. The first weight vector will be gradient of loss with respect to A1 multiplied by the input vector transpose or H naught transpose. And H naught transpose we already know H is 101, so transpose will be 101 but row vector. So this gradient of loss with respect to A1 we can see it in here, and we will get one 3 by 3 matrix which is nothing but gradient of loss with respect to W1. Now next we need to calculate gradient of loss with respect to B1, first bias term, and we already know the first bias term and the first pre-activation are linearly related, so this is why both of them will be equal. So now these were the calculation for the forward pass and backward pass. Now we are going to learn one concept. Why? Well, because after doing this first iteration of forward pass and backward pass, we need to do improvement, and to improve this parameter we will need to calculate the new parameter or new value. Then we will calculate the loss value, and loss value should be less than the previous loss value. That is the method, the correct method to in the forward pass and backward pass. The concept is we are going to update the forward pass, and using the value which we are going to have in the forward pass we will calculate the backward pass. Then we are going to update the new value, and we will calculate the again forward pass, and we will calculate the again loss. So the new loss should be less than the previous loss, and that is how we will go towards our goal matrix. So we already know our original parameter are like this. I have used here dot dot, but you can go back and look at the complete digits if you want. Then we already know B1 was like this. So by calculating, but we have calculated this, both of this, by calculating gradient of loss with respect to W1, and we got the gradient of loss with respect to W1, and we got gradient of loss with respect to B1 like this. This is 3 by 3 matrix, and this is 3 into 1 matrix or column vector. Now, if we take the eta as 1, the new weight vector, the first weight vector should be W1 minus eta gradient of loss with respect to W1, and the first bias term, new bias term, should be B1 minus eta gradient of loss with respect to B1. And W1 is already given, eta is 1, gradient of loss with respect to W1, we can see it in here. And if we use this formula, and we'll get a 3 by 3 matrix, which will be like this. You can do the calculation by yourself. And then the next thing, we need to calculate B1 new, the first bias term, but new bias term, new first bias term, which will be nothing but B1 minus eta, which is 1, and gradient of loss with respect to B1. And we have already calculated this one, this is given, and eta is 1, so we'll get one column vector, which is our new bias term, new first bias term. How to update this? So we need to update this, means we need to calculate a new one, the first pre-activation, but new. So the formula will be W1 new, the input vector 101, and the new first bias vector. And if you do the calculation, we'll get the first pre-activation like this column vector. And we will again use our log function 1 by 1 plus e to the power minus a1, and for each a1 term we will get corresponding h1 term, which will be nothing but a column vector again. And now we will need to calculate a2, but before that we need to calculate b2, because here you can see b2 new. We need to know what is the value of b2 new. This will be nothing but b2, which is already given, and eta, which is 1 already we know, and gradient of loss with respect to b2, which is we calculated earlier. And if we calculate this correctly, then we will get the result of b2 new like this. Now we need to calculate w2 new, but these are similar calculation. We can calculate b3 new also earlier, there is no issue. So just b3 minus eta b3 gradient of loss with respect to b3, and if we already know eta is 1, and if we do the calculation, we'll get one column vector like this. And again, for calculating a2 new, we need to know what is w2 new, which will be nothing but w2 minus eta gradient of loss with respect to w2. We have calculated this figure, gradient of loss with respect to W2, and W2 is already given. We do the calculation, we'll get one 3 by 3 matrix, which is nothing but new second weight vector. And similarly, we can calculate new third weight vector using W3, which is already given in the question, and eta is 1, which is also given, and gradient of loss with respect to third weight vector, which we already calculated, and we will get one 3 by 3 matrix, which will be our new third weight vector. Now using all of this, we can create uh, the new second pre-activation, but the thing was, how do you know the H1 new or H2 new? Well, this was simple, very simple. We have already calculated the A1 value. So from A1 value, we can get H1 value using the log function. So here you can get H1 value using the log function, and we'll get B2 value, B2 new value, and then W2 new value. Next, what is our A2 new? So A2 new, if we calculated this matrix multiplication and we'll add this bias term, we'll get the second weight vector, the new second weight vector, which is also a column vector. And if you use the log function on a new second weight vector, and we will get the second activation. uh, and this is nothing but new pre-activation, second pre-activation. Sorry, I earlier said it is a weight vector. This is not second weight vector. Weight vector is this, but this is A2. A2 means pre-activation, new second pre-activation. This will be new second activation. Using log function on new second pre-activation, we will get new second activation. The formula is 1 by 1 plus e to the power minus a2 new. For each a2 new term, we will get corresponding h2 new term. And now we can calculate a3 new, which the formula it will be w3 new h multiplied by h2 new plus b3 new. We already calculated b3 new using b3 minus eta gradient of loss with respect to b3. This matrix multiplication W3 new we have calculated using W3 minus eta gradient of loss with respect to W3, and H2 new we have calculated using log function on A2 new, and we will get one column vector, and again we will use the log function on each A2 new value. Then we will get corresponding H3 new value, which is our third activation, and it's also the new third activation. Now, what will be our new loss? New loss will be minus log of, again 1 multiplied by log minus minus 1 multiplied by log of where it was the 1 value, the third one, so 0.93. And here I have not written 1 because multiplied by 1 is same. That's not going to change anything. So this will be 0.072, and you can clearly see the loss value have decreased. So if we can see the previous loss, it was 0.856. So, and the now new loss is 0.072. So there's a huge improvement. So thank you.